So double replacement, once again, we're reviewing a little bit, aqueous solution. So these compounds are dissolved in water to begin with. That means being dissolved in water, they're in their ion form. Okay, they're being surrounded by water molecules. And yes, you could produce gases, molecular compounds, such as water. Those ones are a little bit more complicated. We're not going to be looking at in full depth of all the possible double replacements. We're really going to be sticking with looking at the ones that form precipitates or become solids and they fall out of solution in the powder form. All right, solubility rules. I'm also going to, these are a very small, narrow amount of solubility rules. I'm going to post one that's a bigger, better chart for you to follow. One thing to remember about the solubility rules is you're not expected to memorize them. You're going to be, using the chart on the quiz. You're supposed to just be able to look it up, find it, to decide whether or not it's going to precipitate out. So here, once again, soluble means that it's going to stay dissolved in water, that it will not form the solid, it will not precipitate out. And the most notable ones, of course, nitrates and acetates are always soluble. They never form precipitates. Chlorides, bromides, iodides, and sulfates, most of them are soluble. There's a few notable exceptions. Silver, mercury, lead is a big one. We never really use mercury in our lab because it's way too toxic, but lead and silver compounds we do use, and they will precipitate out. For sulfate, it's usually the heavy alkaline earth metals. It's usually calcium, strontium, barium, but here they just list strontium and barium as possible exceptions here. So if you see sulfate with any of those, they will form precipitates. Insoluble, that's a word for saying it forms a precipitate. So just, attach that. Insoluble means it's not dissolved in the water, okay? Sulfides, carbonates, phosphates, and hydroxides. Typically, the majority of the compounds are insoluble, or they will form precipitates. The notable exceptions are ammonium compounds and alkali metals. If you ever see an alkali metal or ammonium in a compound, automatically assume that it's in the soluble category. That's pretty much the same. Calcium, strontium, barium for sulfide, okay? Those ones will stay soluble, and then calcium, strontium, barium for hydroxide also stays soluble. Those are the notable exceptions. Anything else though, you see copper with any of these, you see iron or aluminum or any other metals with them that are not on this list, they are going to form solids and precipitate out. All right, so I think we were here identifying these. So take like a minute or two, go through that list there, check and see, decide whether it's soluble in water or not. The sodium nitrate, barium bromide, lead 2 bromide, magnesium sulfide, and the potassium sulfide. So take a moment to do that, and then we will come back and go over it. Sodium nitrate, soluble in water or not? What say you?
Yeah.
Yes, definitely. We're going to go with yes here. 2 reasons. It has nitrate, always soluble, and it has an alkali metal, always soluble. Both make that always soluble. Barium bromide. Anybody at home? You guys still there? Yes? No? Yes, good. Chlorides, bromides, iodides, the only exceptions are silver, lead, and mercury. So, barium not being one of those exceptions, that is also a yes. Lead 2 bromide. Obviously, I just said that. Lead is one of the exceptions, so that's a no. Very good. How about magnesium sulfide? Sulfides are typically insoluble. Is magnesium one of the exceptions? No. So this one is a no. Very good. And potassium sulfide. Sulfides are typically insoluble, but what is potassium? It's an alkali metal, right? So alkali metals are always important exceptions. This is actually a yes. Yep, definitely. Alkali metal, ammonium in anything, nitrate in anything, acetate in anything. Those four are always soluble. Okay, so I realize this is not necessarily in the paper notes, but you can write it on the side there, at the top next to the chart or on the other side of the paper. But it's in the paragraph form on there. The molecular equation shows each of the substances in the compounds with their physical states written next to the formulas. So this is the basic normal balanced reaction. We call that the molecular equation, even though most of the stuff in there is not a molecule, they are ionic compounds. So the regular balanced equation that shows all of the molecules or all of the compounds written like normal with their physical states next to them is going to be called the molecular equation. So usually for this part, when we're doing double replacement, we write out the molecular. The next is going to be something called the complete ionic. So you write out your molecular and then you look at which ones you need to break apart into their ions. Because remember, anything that has a Q next to it, like these guys right here, remember they are dissolved in water. So they're actually floating around in the water as their ions. They are not attached to anything. So the complete ionic equation shows all of the aqueous compounds as separate dissociated ions floating around in between the waters. So insoluble things that are going to be precipitates or stay solid, they of course don't separate because they just fall to the bottom as the powder, stay like that at the bottom. So anything that's just solid, you would just leave together as the compound. So silver nitrate, we break apart. Silver is +1. This is where you need to really know your charges pretty well. Remember, silver, zinc, and cadmium are the ones in the transition metals that are not MOMs. These guys, +1, -1. Sodium's a group 1 element, so it's +1, and then the chlorine is a halogen, so it's going to go to chloride with -1. Use your periodic table to refresh you, quickly look up the charges. And basically, you just separate the compounds and write them as ions. Nitrate, of course, is one of your polyatomics. So that one you'll find on your polyatomic ion list if you haven't memorized it already. NO3-, the charge on nitrate is always -1. So a good thing to have out too is that list of polyatomics to reference so that you can get the charges correct. Now what happens here, you write out the complete ionic, you separate all of the ones that are aqueous into their ions. And it gets really long. Then what happens is we are going to cancel down to really only looking at exactly what's reacting. Because if you look here, what's actually forming a chemical bond and making a new substance? It's really just the silver ion forms a bond with the chloride ion to give you the solid that falls to the bottom. The sodium and the nitrate are still floating around in between the waters, and we call them spectator ions because they're kind of just watching the show. They're watching the reaction happen, they're not doing anything. So when we do this, we write out our complete ionic so that we can cancel out our spectators, and that leads us to the net ionic equation. The net ionic equation shows only the things that are actually reacting. Everything else is taken out. Sort of like reducing it down to only the important stuff. And in most college level chemistry here, they're more interested in the net ionic than they are the molecular because you're really concentrating on what is actually changing here. So we're going to do some practice here. And we're going to write out the balanced molecular, the complete ionic, and the net ionic. Now once again, you need to have that periodic table out so that you can look up the charges very quickly, so that you can rewrite the formulas correctly, and then you can balance it correctly. Also, reference the solubility rules because we need to check and see if anything's going to precipitate. Okay? So that's how I always start off, and I start looking at the charges here. So barium and barium chloride, what is its ionic charge going to be? What group is barium in? It's in 2, so it goes to +2. Chlorine, halogens, they're always what? -1. Here we go. Yes, -1 there. Potassium. +1. And nitrate. Off that lovely polyatomic chart. It's -1. Good. All right, now that we have those, remember in a double replacement, the cation of the first compound combines with the anion of the second. The cation of the second combines with the anion of the first. That's how the switching goes. So we have to combine barium with nitrate and write that formula out correctly. So how many of each do we need to write the formula? Because remember, the charges have to add up to 0. So how many bariums, how many nitrates? 1 barium, 2 nitrates. Exactly right. So that's what we're going to put here. BaNO3. Don't forget your parentheses. Like so. That's going to be our first product. Now, the potassium combines with the chlorine here. What is that formula going to look like? +1, -1, one of each. Pretty easy. So we put that here, KCl. Doesn't really matter what we do next. We can balance or we can check for solubility. Which one you want to do first? Balance. Let's go for balancing. All right. So we've got 2 CLs. We've got 2 nitrates here. Doesn't really matter which one we start with. We could do that first. Put a 2 there. That means that we need a 2 here. And then we would, no, don't need a 2 there because we have 2 of the nitrates. So we have 2 nitrates, but we need 2 potassiums and we need 2 of the chlorines to make that work. That's 2 CLs and then 1 nitrate, 1 potassium. So we write that out. Now let's check for solubility. Barium nitrate. Is that going to be AQ or solid? And feel free to respond in the chat. Barium nitrate, AQ or solid? AQ, very good. So we put this here. I have to put it small because I didn't space it out good enough. Potassium chloride, AQ or solid? AQ. Good. Well, this is an interesting one. Everything in it happens to be AQ. Aqueous, staying dissolved. So we write out our complete ionic. We're going to break everything up into its ions, and we're going to balance the ions as well. So not only do you break them up, but you also have to balance them. So if the barium chloride breaks up, you're going to get 1 barium, like that, plus, since there's a 2 here, you're going to get 2 of the chlorides. So every time that formula unit breaks up, you get 1 of the cation, 2 of the anion. So make sure that you balance them out from their formulas or from their coefficients. So this is going to be Ba2 plus 2Cl minus. That's our first reactant. So formula unit, break it up that way. Now for the second compound here, we have 2 potassium nitrates. So we do have that coefficient of 2 in front of it, so we still need to maintain that balance. So for that one, we're going to break apart as well, but we are going to make sure that we balance, so we're going to keep that 2 in there, so there's going to be 2 K pluses and 2 of the nitrates, like so. That's the reactant side. Now let's look at breaking up our products. So over here for the products, we have the barium nitrate. Once again, that's a formula unit where we're going to get 1 barium ion and we're going to get 2 nitrate ions once it dissolves. It's going to break apart into that. And last but not least here for the potassium chloride, once again has the 2 in front, so we're going to put that out there. 2 K pluses and 2 Cl minuses, like so. What you'll notice in this particular one, everything stays an ion, nothing precipitates out. So for our net ionic, it's basically no reaction. You can write it like that, no reaction, or you can write it as no precipitate. Either one would be acceptable. And that's how we would see that particular problem. Now I'm going to do number 2 with you, and then I'm going to let you practice for 3 and 4. But let's go ahead and take a look. We've got sodium hydroxide, aluminum chloride. First and best way to do this is looking at the charges, because you got to figure out how to write the formulas for both products. And yes, the sodium is going to combine with the chlorine. The cation of the first combines with the anion of the second. That means the aluminum is going to combine with the hydroxide. Now, charge on sodium. What's sodium going to be? +1, very good. Alkali metal, +1. Hydroxide, what's the charge on hydroxide? It is -1. Now, if you've already determined too that sodium's +1 and it's 1-to-1, then you obviously know that hydroxide's got to be -1 as well. So you don't really have to identify both charges that way, but you can look up one and then you can figure out the other. That's also helpful. Aluminum, what's the charge on the aluminum? It is +3, group 13, yes. It's going to be +3. And then as you can see, there's 3 chlorides. So what's the charge on the chlorides? Going to be what? -1, good, because we have 3 of them, so that adds up to 0. Exactly right. Now that we know their charges, we can do the correct formula writing. So sodium goes with the chloride. That's easy. That's +1, -1. NaCl, not too bad. But the aluminum is going to combine with the hydroxide. So that one is a +3 and a -1. How do those combine? How many aluminums? How many hydroxides?
3 hydroxides and 1.
Good. 1 aluminum. That means we need parentheses around our hydroxide. Put the 3 outside. Keep the group together. Now we can look for balancing. Let's balance, and then we'll do solubility rules. What's out of balance? The chlorine and the hydroxide. Very good. So we start here. We can put a 3 here. See that, to balance out the chlorines, that means sodium needs 3, hydroxide needs 3, and guess what? Sodium and hydroxide are together, so we put the 3 there. That's nice. Works out good. Solubility rules. NaCl. Hopefully you just know that one off the top of your head. Does salt dissolve in water?
Yes.
Yes, it does. Okay. So we put our AQ here. Aluminum hydroxide, though. That one probably you would need your rules to look up. Hydroxides are typically what?
Insoluble.
Insoluble. Is aluminum one of the exceptions? No, it is not. So this one definitely forms the solid. So we get aluminum hydroxide solid, falls to the bottom. I believe that one's a white precipitate, white powdery stuff. Now we're going to do the complete ionic, where we only break up the AQs. So in this case, we only have to break up 3 into their ions. You do not have to break apart the solid because it's not dissolved. It's not in the ion form. Once again, maintaining the balancing of the different ions, we have to do that. So the 3 in front here means I have 3 sodium ions and I have 3 hydroxide ions when that breaks apart. So this would be 3 Na plus, 3 OH minus. On this second reactant here, still going to maintain that aluminum chloride formula unit breaks apart. You're going to get 1 aluminum. That's at 3 plus. But because there's 3 of the chlorides here, we're going to get 3 chlorides, like so. Over here, the first product that is aqueous, maintaining the balancing here, so we put 3 sodiums and 3 chlorides. And then because this is the solid, it just stays together. And put the little S there, I'm running out of room. Now, in order to write out the net ionic, it's just canceling. We need to figure out what our spectators are and get rid of them. So which ions are the spectators? Which ones are on both sides as ions that are not actually reacting or forming a bond?
Sodium.
Sodium. Good. And the other one? Chloride. Good. So we're going to cancel those out. What are we left with? We're left with the aluminum, we're left with the 3 hydroxides, and then the aluminum hydroxide solid. Now, just being a little bit picky, we always write the cation first. So you would put the aluminum first, then the hydroxides, and then you would write out the solid together, like so. Cation always comes first. Although technically, if you wrote the hydroxides first, I probably would not take off a point, but you will not see it written the other direction in a textbook or online. It will always put the cation first. All right, so now it's your turn. You have 2 to work on, 3 and 4. We'll come back in about 5 minutes, check on everybody. All right, so looking here, just going to go through. Hopefully you can correct as we go. This is going to be +1, -1, +1, -1. That's nitric acid. Just remember, acids, H is always +1 as the cation there. Hopefully you figured that out. The sodium's going to combine with the nitrate, NaNO3. And the chloride, of course, is going to combine with the hydrogen, forming hydrochloric acid. All right, then balancing. How we are with balancing. It's already balanced, very good. Okay, now solubility rules. Sodium nitrate, AQ or solid? AQ, very good. And hydrochloric acid, or if you're looking at the chlorides, the 3 notable exceptions are silver, lead, mercury, so this is obviously AQ as well. Acids, by definition, are dissolved in water, so. Complete ionic now, just break everything apart into its ions. So we get the Na plus, Cl minus, plus the H plus, and the NO3 minus. And over here, they're just in a different order. And I'm going to run out of room, but that's okay. And what do we notice about this one? It's a, what type of reaction here, if there is one? It's a no reaction, no precipitate, so this one doesn't actually have a reaction. You can write either one, it doesn't really matter. Means the same thing. not too bad, pretty easy. Now we have one, obviously, that's going to need a little bit more balancing here. Sodium's +1. Anybody look up carbonate? What's carbonate? It is 2-. Calcium, definitely not a +1. It is +2. It's in group 2, alkaline earth metal. Or you could look at the chloride here, which is -1. You already know that, so since there's 2 of them, that means the calcium has to hold a charge of +2. Now we need to recombine them. Sodium goes with the chloride, that one's easy, NaCl. And then the calcium with the carbonate, +2 -2, that's a nice 1-to-1, CaCO3. All right, balancing. Are we balanced? No, because we have 2 of the chloride, 2 of the sodium, but it's an easy fix here. All you have to do is put a 2 there. Nice and fixed. Now solubility rules. Let's look here. Sodium chloride. Aqueous, very good. And the calcium carbonate. This is a solid, very good. Carbonates are typically insoluble. Actually, that's what's in limestone, by the way, calcium carbonate. The carbonate exceptions, I believe, are just the ammonium and the alkali metals. So, since calcium's an alkaline earth metal, it is definitely insoluble. Now we break apart our ions. So, formula unit-wise, there's 2 sodiums for every 1 carbonate there. Carry that 2 out in front of the sodiums. And the carbonate gets a 1 for that first one. Here, we're adding in the 1 calcium and the 2 chlorides, like so. Over here, using the balanced part, we're still going to have 2 sodium ions and 2 of the chloride ions. And then this one's the solid, so it stays together. Like so. Spectators. Who are spectators? Sodium and the chlorine, they go away. What is left is going to be our net ionic. It's the calcium, writing the cation first, reacting with the carbonate. That's going to give you the calcium carbonate solid. Like so. Any questions? Hardest part of predicting products, I'd say definitely the most challenging of the bunch.